last topic of the unit was projectile motion. We saw over the last couple of days that we have two types of projectile motion questions that we can and that we will see. On our unit assignment, we saw both types of projectile motion questions. Pretty good chance on our test exams, we might see both types of projectile motion questions as well. The first type is when we launch an object horizontally off the edge of a building like this. Maybe it's moving at 10 meters per second. Maybe it has an initial height of 30 meters. But it leaves the edge of that building or the edge of that cliff. What's the shape of that path going to be? Yeah, it's half a parabola, right? We call it a parabola. Now, the other type of projectile motion question we see is when we launch it at an angle right here. Let's say, again, it's 10 meters per second. Let's make our angle, though, let's say 60 degrees. We're going to launch that. It's going to go up into the air like this and then come back down. What's the shape of that path? Yeah, that's a parabola as well. In fact, if you look at the right-hand side of the second diagram, it should look the same as the right-hand side of the first diagram. It's the second half of the parabola. It's just the second one has the trip up in addition to the trip down. Now, if we want to analyze this first problem, we're going to break it up into x components and y components because it's moving on both the x-axis and the y-axis. What equation are we going to use to describe the x component of the velocity? Always. There's no exceptions to this, Parker. Yes, velocity is equal to displacement over time. The reason we're going to use that equation is because... Nick, how come I'm going to use v equals delta d over delta t, my group A equation, my constant velocity equation? How come we're going to use it? No, we don't. In fact, we don't even have the horizontal displacement, right? How come we're going to use this equation? Forget about the givens for a sec. Yeah, come. Yeah, it's moving at a constant velocity horizontally. So we're going to use our constant velocity equation. In fact, over here, it's the exact same thing. Constant velocity horizontally, so once again, we'll use that constant velocity equation. Now, the y component involves acceleration, involves gravity, right? So it's accelerating. It's speeding up as it goes down, slowing down as it goes up into the air. What equation, Braden, do you want to use for the y component? Good. D is equal to VIT plus 1/2 AT squared. We're going to do the same thing over here. The reason we're going to use that one is, well, A, because it's an acceleration equation, one of the many acceleration equations, but specifically this one we're going to use because it is the equation for a parabola, and that's the shape of my path. It's a parabola. So that's what I'm always going to try first. Now, let's point out the differences between these two questions. Okay, first difference, the horizontal velocity here. The horizontal velocity, in this case, is 10 meters per second. The horizontal velocity here is not 10 meters per second. What is it? Don't know. We got to find it, right? How are we going to find it? How are we going to determine what the horizontal velocity is? Yeah, Amelia? Get rid of the funny angle. So take that 10 meters per second up. Good. And then call that x, call that y, and call that 60 degrees. We use cosine 60 is equal to x over 10. That equals 8.66. We say sine 60 is equal to y over 10, opposite over hypotenuse, gives me 5.0. Let's box that off. Just do what we do every time we see a problem with a funny angle, regardless of whether it's a add displacements or regardless of whether it's a projectile motion question. What's the x component of velocity now? Aoife, do you have that one? How much of that 10 meters per second, which, by the way, is dead to us now, right? How much of that 10 meters per second is x component?
That would be 0.
No. The x component of this 10 meters per second, anybody else? Yeah, Andrew? 8.66. Does that make sense either? Right, we took away that 10, but part of that 10 is x component. Well, 8.66 of it is x component. Now let's take a look at the next thing that's a little bit different. That's going to be delta d for the y component. Delta d for the y component. Delta d for the y component in this first question is what? Well, in one of these problems where it's launched off the edge of a building, it's always going to be negative something. What is it here? Yeah, we're going to make it negative 30. Negative because it's down from where it started, right, Luke? Now the y component of the displacement for the second problem, what's this going to be? Change in position, where it lands relative to where it started, Nick? No. Zero. The displacement is zero because it starts at ground level and ends at ground level. Finally, the third difference between these two questions is VI. VI for the y component here is zero. Somebody said it. And VI for the y component over here is, what is this one, Nick? 5 meters per second. If you can recognize these things, you've got a fighting chance at any question that you see. Okay, now it becomes a matter of algebra, just sub the numbers in and rearranging and solving for something. And I'll tell you what, if you get this far and are able to sub the right numbers in, even if you rearrange it wrong and get the wrong answer, you're still going to get significant marks, significant part marks on this. All right? So know how to do this. And then if hopefully you're able to do the algebra well as well and get 100% on the question. But even if you're not able to do the algebra, at least you can get a pretty good mark on the question because you knew what to do, you knew what variable was what, you just had trouble with the math, right? All right, let's take a look at our two questions that we had for homework. They were questions 6 and 7 on worksheet number 9. I want to do both of these questions today, starting with number 6. The ball is thrown from a height of 2 meters at an angle of 60 degrees, speed of 10 meters per second. Okay, now it's caught by another person at a height of 2 meters. So here's a person, let's say it's caught by another person over here at a height of 2.0 meters. We want to know the time of flight of the ball. We want to know how far it lands, how far downfield it lands, and the height of the ball at 0.80 seconds. This is a good question, actually, C especially. We got a funny angle. We got to get rid of this. 60 degrees, 10 meters per second. We're going to say x is equal to 10 cosine 60, which is 5, I think, isn't it? 5.0? And y is 10 sine 60, which is 8.66 meters per second. And cosine for x, sine for y. Now we do our x and y components. V equals delta d over delta t. What's the horizontal displacement? Colleen, what's the horizontal displacement? The horizontal velocity I meant, sorry. The horizontal velocity is 5 meters per second, good. The horizontal displacement, how far does it go horizontally? We don't actually know, do we? What about the time? We don't know that either. Okay, so let's go to the y component. Using the equation that we always try first. The vertical displacement is what? 0. Somebody said 0. Isn't it 2 meters? It started from 2 meters. Well, it does start from 2 meters. Where does it end? 2 meters. So what's the change in position? 0 meters. VI for the y component, VI for the y component is 8.66. Good. And the time, we don't know that. Plus 1/2 of A, which is negative 9.81, times the time squared. How do I get rid of the one time there? How do I simplify this to get time only in one place? Yeah, divide every term by time. What's 0 divided by time? 0. What's time divided by time? 1. 3 divided by 3 is 1. 7 divided by 7 is 1. 12 divided by 12 is 1. T divided by T is 1. So 8.66 times 1 is 8.66. Half times negative 9.81 is negative 4.905. What's T squared divided by T? T. So it becomes 0 is equal to 8.66 minus 4.905 times T. Take this over to the other side by subtracting. And then how do we get rid of the 4.905? Some people think that, oh, because there's a negative in front of it, we have to add it, right? But how is it connected to the time? It's multiplied, so we're going to take it over, Emmerich, by dividing it, right? So we're going to say 8.66, or really it's negative 8.66, divided by negative 4.905 gives me a time of 1.7655 seconds. Now, I want to write down that unrounded number, but because I'm looking for the time specifically in A, I'm going to also round it to 2 digits. Okay, so 2 digits, 1.7, is it 1.7 or 1.8? Underline your first 2 digits, put a little arrow underneath your next digit, and look at the arrow and say, is it a 5 or greater? Yes. So therefore, we round from 1.7 to 1.8 seconds. Now let's take this and sub it into here. Nice thing about your TI-84 calculator or your TI-83 is that it stores that unrounded number in it, 1.7655 seconds. Multiply that by 5 to get it to the top, and we end up with 8.8277 or 8.8 meters. Okay? How might I find the height of the ball at 0.8 seconds? How do you think I'm going to find the height of the ball at 0.8 seconds? What am I looking to solve for there, Luke? Yes, yes. So some people are going to look at that d is equal to VIT equation and say, well, no, the displacement is 0. Like, why would I solve for the displacement? Because it's 0. The displacement is 0 after 1.76 seconds. What's the displacement after 0.8 seconds? So let's do this again. But this time solve for a different variable because we have a different time. D is equal to 8.66 for my initial velocity y component. My time was it 0.8? 0.8 seconds plus 1/2 of negative 9.81 times 0.8 squared. I get 8.66 times 0.8. 6.928. Let's add to that, brackets 0.5 times negative 9.81 times 0.8 squared. 3.8. So the height of this thing at 0.8 seconds is 3.8. Make sense? Now you understand that it's going to be at 3.8 meters twice. Oh, wait a second. That's not right. That's not the answer. What are we going to do, Amelia? Yeah, this is my displacement, 3.8 meters, but I started at 2 meters above. So if I want to find the height, what did I say that was, 3.8? If I want to find the height, then I'm going to add the initial height to it, which gives me 5.8 meters. Does that make sense? Yep. It could be like that's a harder one, but it's not insane. That would have been kind of a trick to do for you, to do with you without kind of giving you a jump on that now, right? If I gave you that for the first time on a test, but generally the questions on tests, I'll say, are generally not easy, but generally of the more straightforward variety, usually, because I'm not trying to test to see, like, I'm not trying to trick you. I'm trying to test to see if you know stuff, right? So generally, they tend not to be the trickier ones. It's not to say that you couldn't see something like that, but they tend not to be something like that. Okay. All right, so I want to take a look back at our original diagram here for a second. There are two times when it's at 5.8 meters. Okay, it's at 5.8 meters right here, and it's at 5.8 meters right here. Agree with that? On its way up and its way down. Our time here is 0.8 seconds. 0.8 seconds. Can you tell me which one this is? Okay, it's at 5.8 meter height in position 1 or position 2 at 0.8 seconds. Why do you say 1, Andrew?
Because time is the scalar, so it's always moving forward.
Okay, yeah, time is always moving forward, but displacement is 5.8 meters in two places. So at two different times, it's at that height of 5.8 meters. So it has nothing to do really with vector or scalar. Yeah. Okay. I'm asking for 0.8 seconds. This is how we found that height of 5.8 meters, right? At a time of 0.8 seconds. It's at a height of 5.8 meters. But is this 0.8 seconds or is this 0.8 seconds? Because it's at that height in both cases, right? On the way up and the way down. One of them occurs at 0.8 seconds and one of them occurs at something else. No, no. Gravity affects it equally on both sides. Yep. Than it is to come down? No, no. In fact, it's going to take the exact same amount of time to come up as to come down because there's only one force acting gravity, right? So? Yes. Braden, is that what you're going to say too? Yeah. It's 0.8 seconds. The total time that it took to go from here to here was 1.8. 0.8 is less than half the time, right? So that means it must be on the trip up. Does that make sense? It's half time is like 0.9 seconds. So that second one is going to be somewhere around 1 second, probably. Does that make sense? That's a little bit more than you're going to have to be able to do on a test, but it's still good to get our minds going like that, right? Okay, let's take a look at the next one, number 7, the last one on that worksheet. Rock is thrown at a speed of 30 meters per second, an angle of 40 degrees. Rock lands at the same height as it's released. What's the time of flight of the rock? How far away does the rock land? And what's the max height that the ball attains? That's a good question. That is a good question. Trick question. Okay. It's supposed to be a rock, but all of a sudden it's transubstantiated into a. It's the rock has become a ball somehow. The rock / ball is 30 meters per second here at 40 degrees. The rock / ball follows a parabola. The rock / ball has an x and a y component that we have to resolve. We're going to say cosine 40 degrees is equal to x over 30. 30 cos 40 is what? 22.98. 22.98, thank you. And the y component we'd find by the sine function, 30 sine 40. What does that one equal? 19.282 meters per second. Good, thank you. So that rock / ball, whatever it is, He's moving at 22 meters per second horizontally initially and 19 meters per second vertically initially. All right, now we do our x and y component thing. Always v equals delta d over delta t. The x velocity is, what's the x velocity? 22.98 meters per second, good. Horizontal displacement, I don't know. Time, I don't know. Let's go to the y component. D is equal to VIT plus 1/2 AT squared. What's the vertical displacement? What's the vertical displacement here? Aoife? Or Amelia, I mean, sorry? 0? It is because it lands at the same level as it started, right? VI, since I was calling on Aoife there, and called Amelia Aoife. Aoife, can you tell me what VI is for the y component? 19.282, good. Don't know time, plus 1/2 of neg 9.81 times time squared. Simplify a little bit. Half times neg 9.81 is neg 4.905. Now, do you guys know what I'm doing if I just cross those off? I'm dividing each term by time, right? I'm just not quite showing the dividing by time. 0 divided by time is 0. 19.282 times time divided by time is 19.282. And 4.905 t squared divided by time is 4.905 t. If that bothers you what I just did, just do it the way we were doing it. Show everything, okay? Solve for time there. Negative 19.282 equals negative 4.905 times t. Do the division there. What do we get? 3.931 seconds. Which we're going to round to, how many digits should that be? Back to our data, looks like 2 digits. 3.9 seconds for question A. Then what do we do with that, huh? Ethan A, what do we do with that? Yep, sub it into there. The unrounded number, right, into there. Take that number that we just got and multiply it by 22.98, and we're going to get a displacement of 90 meters now. Okay, 2 of 3 done now. Now we just got to look at C, how far this rock/ball goes vertically into the air. What's its max height? How do we do that? I think somebody yesterday gave me an idea. Yeah, that's the idea that somebody gave me yesterday. Divide t by 2. So my time was 3.9 seconds. At 1.95 seconds, we're at max height. So find the displacement using this equation at 1.95 seconds. That works. What's the other way? That works every single time, assuming it lands at the same level as it started, because the max height would occur halfway through. Now, if you had a question, and I'll let you know a little secret, in Physics 20, you're not going to get a question like this. But if you had a question where it landed on the ledge of a building or something, then it wouldn't be at max height at half time anymore, right? Does that make sense? So this method works beautifully for these questions. It's not as general as the other way, the way that I showed you, though. The way that I showed you works all of the time. Yeah, go ahead, Luke. Yeah, let's try VF squared is equal to VI squared plus 2AD for the Y component here. Luke, you watching this? VF squared is equal to VI squared plus 2 times A times D. Andrew, how fast is it moving when it reaches max height? Yeah, it's stopped, right? Vertically, it's stopped when it reaches max height. 0 squared is equal to 19.282 squared. And then we solve for the displacement. Right? Okay, so now let's solve for that. 19.282 squared comes to the left side by subtracting. Then we divide by 19.62, which is 2 times 9.81. 18.9 meters, 19 meters. So the maximum height is 19 meters. We good with that? Yes? So this is a bike ramp that a neighborhood dad and I set up last summer. We set up this bike ramp for my 7-year-old and his 2 kids, one of whom was 8 and one of whom was I think 5, and then a few other neighborhood kids. There was 7 or 8 neighborhood kids around. Okay, you set up this bike jump. So the other dad and I, we decided we have to test it out first, and we do. And I don't have video of this, unfortunately, but we test it out perfect. I go over it like 6, 7, 8 times perfectly. Go up here, go pretty fast over there, get a good jump, and follow a parabolic path and land down here somewhere, right? Well, then I decide, me and the other dad decide, let's make it a little higher. So I make it a little higher. Not crazy high still, higher than what we see here. I don't have a picture of the last version of it. It's higher than what we see here, but it's not crazy high. We make it, I don't know, maybe like this high. If you notice this board, it's actually 2 pieces of plywood that are screwed together. So it's actually kind of got quite a bit of flex to it, quite a bit of bend to it. So I decide I'm going to bike to the end of the street there, and I'm going to give her as fast as I can and go over this thing. And when I do, you see that instead of launching at maybe 20 degrees right here, what happens is this ramp bends, it bows, and then it goes more like this. So I'm launching at, I don't know, maybe 60 degrees and following a parabolic path like this, right? Now, you probably know where this is going. It did not end particularly well for me. And as soon as I left that jump, I knew it. I knew it wasn't going to end well. So I ended up landing on my front wheel, my front tire. And of course, if you land on your front tire going down that quickly, it's not going to end particularly well. I landed on my front tire. My front tire actually looked more like an egg than it did my front wheel, I should say, looked more like an egg than it did a wheel after this was done. An egg, and it was bent, twisted the other way as well, not just like squeezed in, but twisted that way as well. The end result of this is the kicker. The end result of this was this. That's my collarbone. That's one piece of my collarbone. That's another piece right there. That's another piece. And that's another piece right there. So that was last August. Last August, my collarbone was in 4 pieces as a result of this. My helmet, by the way, was in 3 pieces. I don't know.
Should have took a video and posted.
This is the post. This is the post result. 4 days later, the 4 days later result. For 4 days. For 4 days, they made me walk around in a sling with my collarbone in 4 pieces. And then on the 4th day, they did a little surgery and put a little plate in there with 11 screws in there, which are still there, which I can actually feel right now, these screws sticking out. I'm not going to make anybody do it, but I can feel a screw right here. Yep. Yeah, you can. Now, kind of, yeah. Now, the moral of this story is, well, wear a helmet, because it's not don't do it. Everybody said, like, you're too old to do that. And I'm like, no, I'm not too old to do that. Like, if old people like me don't do stuff like this, then we're going to start feeling old. I don't want to feel old. I want to feel young. And every once in a while it backfires, right? Every once in a while you're doing something to stay young and it backfires, and this is what happens. But it didn't have anything to do with being old. Like this could have happened to a 20-year-old or a 7-year-old as easily as it could have happened to a 47-year-old. Wear a helmet like I did, because the helmet broke into 3 pieces as opposed to my skull breaking into 3 pieces. But the other thing about this is, what I wanted to show you is, in a non-idealized situation, what does projectile motion really look like? Okay, so you're launching, let's say we're launching me off of a ramp, okay? Ideally, it follows a parabola. In the real world, do I follow a parabola? If we had a bike, a video of a bike going off a jump and spinning around, I didn't, by the way, didn't spin around. Like when I went over here like I went over here relatively stable like this, except I came down front wheel first. It wasn't like my bike was doing this and I was going head over heels, right? It wasn't like that. At least I don't think so. It would have been epic. This is pretty epic too, though, actually. But what if I was? What if I was going head over heels? Is that still a parabola? Well, we all have something. Everybody and everything has something called a center of mass, a center of gravity. Do you guys know what that is? It's where our mass can be considered to be concentrated. I have a mass of about 70 kilograms, and it's spread out all over my body. But the center of my center of mass, where all my mass can be considered to be concentrated, is about at my belly button. It tends to be a little higher on men than it does on women. Women tend to have a center of gravity a little bit lower, somewhere around their hips. Okay? There are exceptions. Okay? Some men have a lower center of gravity, some women have a higher center of gravity, but on average. And every person, even between 2 men, have a slightly different center of gravity. Okay? So my center of gravity, what I want you to understand from this is that my center of gravity, no matter what my bike and what I looked like as I was going over this jump and doing whatever was happening here, my center of gravity followed the parabola. The rest of my bike might have done whatever, but my center of mass the entire time followed a parabola. So if I had a big red dot painted on my belly button, and we had video of this, we would have saw a perfect parabola of that big red dot on my belly button. It might not have looked like a parabola for parts of my bike that were wobbling or turning or whatever, but for that dot that was painted on my center of mass, it would have been a perfect parabola. Does that make sense? So if you get a question that involves somebody on a bike or a car going off a cliff or something like that, really what we're asking is, where did the center of gravity land? What was the path of the center of gravity, and so on? Does that make sense? It doesn't need to complicate things. Okay? It is, in an everyday practical situation, it is a parabola, but for the center of gravity or the center of mass.